Very exciting class today. We get to learn derivatives of exponential and logarithmic functions. Now, the number e is exciting just like the number pi. These are special numbers. You know, pi and e are things called transcendental numbers. They've got like a special name even associated with them. You know that pi is important because it relates to the diameter and the circumference of a circle. But up till now, you did e when you did logarithms, but you wondered why did they introduce this weird number in logarithms? Why is it that your calculator has log base e and log base 10? Why do they choose this weird number? Well, e is special for calculus because if we look at our graph of e to the x. And this is the same app that I have looked at when we did our derivative for sine, when we did derivative of cos. What is the derivative of e to the x? So first of all to note, I've started it right at 0 when x is 0. When x is 0, e to the x is equal to 1. And it just so happens that at that point, the slope of the tangent is also equal to 1. Now, as I move this point along and draw the derivative graph, I want you to think about what you notice. Feel that, there we go. Nice. What do we notice? It's exactly the same thing. The slope at every single point on the graph of e to the x is exactly equal to e to the x. And it's the only function that that happens to. So if you know that y equals e to the x, then the derivative is equal to e to the x. Which is more confusing than you would like to think, because you're going to get into some complicated derivatives, and one of the parts of those complicated derivatives is to do nothing. Keep it the same. And that feels sometimes a little bit hard to do. But the derivative of e to the x is itself. So if we go to some examples, if you put a constant in front, what's the derivative going to be? Feels like you've done something wrong because you haven't really done very much at all. But that constant in front doesn't affect any other function, so it's not going to affect the derivative of e to the x either. If you were asked to work backwards, what would we have had originally? Well, 4e to the x would have stayed 4e to the x. You ready, Riley? Plus, here we would have an x to the 5. What number would have to be in front? A 3. And then that is an example of a function. Or if you wanted to add 88 at the end, perfect. Well, infinity isn't technically a number, but you could add different things like big numbers, like if you wanted to write 1 million there, or 2 million, or whatever. Could you add a complex number? I don't know about that, because we find out later that we define the constant that you could add as being part of the real numbers, not part of the complex numbers. So this could be any number in your real numbers. I'm not sure that we could put any number from your complex numbers in there. But that's a good question. Ooh, fun. Okay. So find the equation of the tangent line at the point 0, 1. This is what our original graph did, right? Our original graph started with that one point at 0, 1 and drew that tangent line right there. So we would do this the same as we found all of our other tangent lines. We find our derivative. Well, our derivative is e to the x. At x equals 0, y prime will be e to the 0. Y prime will be 1. That tells us that the slope of this line is equal to 1. So if we wanted to find the equation of this line, y equals mx plus b. We know the slope is 1. We know that the b value is our y-intercept. Well, because we have the point 0, 1, it's already telling us that our b value is 1. So here is the equation of our tangent line. So this class is also exciting because some of you already knew that the derivative of e to the x was e to the x, but you haven't done other powers. So what's the derivative of y equals 2 to the x? Well, according to the formula that we have here, it's telling us that y prime should be 2 to the x and then multiply by the natural log of 2. So the question is, why does this work? So I'm going to give you a little proof of why this works. I'll use 2 to the x as a number, but the way to figure this out is for us to try to write 2 to the x as e to the something. Okay. How would we go about doing that? Well, I'm going to start with y is equal to 2 to the x. And this would work with any base. So you could do this generally with b to the x, but I sometimes find that using numbers helps people see things better. This is our goal. Our goal is to write 2 to the x as e to the something. And then I'll show you how that works from there. So what I could do here, we're using logarithms, is I could take the natural log of both sides. If I take the natural log of this side, I get natural log of y. If I take the natural log of this side, I get natural log of 2 to the x. What do you know about your log laws? What could you do with that x? It could come, that exponent could come out in front, right? So all I've done is taken that exponent out of the log and put it in front. If these two things are equal, does it make sense that these two things would be equal? Yes? And what is e to the natural log of y? Well, since those are inverses of each other, they cancel out and we just get that y is equal to e x to the natural log of 2. What does this mean? What was y originally? Y originally was 2 to the x, and now we've played around with it, and now we've got y is equal to e to the x natural log of 2. So we just showed that 2 to the x is equal to e to the x to the natural log of 2. Now, Mr. JR, why should we do this? What is the purpose of this? Well, if I instead had this, and you know that the derivative of e to the x is e to the x, we can do the derivative of this. But this is a chain rule. Can you see that there's a function inside of the e to the x? That this is inside of e to the x. So when we go to think what's our inside function, well, that's in the red box. What's our outside function? That's e to the x. So if we do the derivative of our outside function first, the derivative of e to the x is e to the x. So it doesn't change. Keep the inside the same. Multiply by, what's the derivative of the inside? Natural log of 2. So our derivative is equal to, well, remember that this whole part was just 2 to the x, written in a different way, times by the natural log of 2. And that's what the general rule is. When doing the derivative of any base to the x, you keep that base the same and then multiply by the natural log of that base. And what we did underneath was sort of a proof of why that works. Yes? No, you won't have to. Well, not this year. Maybe in your university classes they'll may ask you to prove some things, but this is the idea. If you had to prove it, what would we do? We'd just change all of our 2's, to fancy looking b's. Oh, there we go. There's a fancy looking b. Did those look like bees? Fancy bees. Oh yeah. I'm going to start making all my bees like this for the rest of the year. How would you write them? You'd go like this? Yeah, okay. Here we go. Best bee ever. Okay. Oh yeah. Worst tea ever, best bee ever. Excellent. Okay. So now we can do derivatives with our new derivative rules. What's dy dx here? Well, 3 to the x stays the same, multiplied by natural log of 3, plus, bring the exponent out in front, subtract 1 from the exponent, just becomes 10x. No problems. Go back to our graphs. So if e to the x was so nice and stayed the same, does something special happen with the natural log of x? Well, let's start dragging this around. Oh. Now you have seen this graph before. Can you recognize it? It was one of your parent graphs that you had to use in grade 12, but it's not all of it, but it's part of it. It is the positive side of 1 over x. And so when looking at our derivative of natural log of x, we write that the derivative is 1 over x. True that since the domain of natural log of x only makes sense when x is bigger than 0, that domain would then transfer to your derivative that you only have the positive side of the 1 over x graph. But generally, when we're doing these questions, we don't go then and add the domain. We'll just write that the derivative is 1 over x. But it does make sense that you can't draw a tangent line to something that doesn't exist. So it is true that this only makes sense for positive values of x. Now, this one too, whereas e to the x is confusing because nothing changes, the derivative of the natural log of x is confusing because it looks so different than what you started with. So if you had 5 natural log of x, this is going to be 5 times, well, the derivative of the natural log of x is 1 over x. So you could just write this as 5 over x. Now, if the derivative of the natural log of x is 1 over x, what do you think the derivative, pick a number, of log any base of x is going to be? Again, For those of you that have seen derivatives of natural log of x, you haven't seen this yet. This is new. Can you tell me how you could write log 3 of x using natural logs? It's not, no, it's not, it's not equal to ln 3x. Because ln has a base of e. So how do we change the base of 3 so that it is a base of e? There's a theorem that allows you to change bases. Do you remember what the theorem was called? The change of base theorem. Wow! They did such a great job at naming these things. So if you use the change of base theorem, which is still up on the board over there, that log am equals log am over log ba, or log bm, I'll write it out. Log b of m is equal to log a of m over log a of b. And I might have switched the letters. Yeah, I did. But the letter switching doesn't matter. What it means is if you have a base b and you want to change to a new base of anything you want, notice that the green part is only on the right-hand side of the equation. That green highlighted part is only on the right-hand side of the equation, which allows you to change it to whatever you want. You can change log base 3 of the x to, wait for it, log base 88 if you want. Okay? But here we want to change it to a log base e. So we'll make this an e, which says y is equal to the natural log of x divided by the natural log of 3. The natural log of 3 is a number. You can type it into your calculator, you can push enter, it'll tell you the decimal places and everything. What does that mean? That means that we really have 1 over the natural log of 3 times by the natural log of x. So when we do our derivative, this would stay because it's just a coefficient, and the derivative of this is 1 over x. And that is exactly what it says here. I'll go back. Okay, I know. I got excited. There we go. Oh, I do have to make a slight change to the notes. Tell me when you're ready. Are we good? Can I scroll back up? Okay. Sorry about this. There we go. That's better. Okay. Whew. And this is what it has right here. Doesn't matter what base you have, you're still going to have the 1 over x, but we saw the reason why that natural log of b appears on the bottom. Again, I'm not going to ask you to prove this, but I sometimes find if you go through the logic of where it comes from, you find that you're able to memorize it better or remember it better. So, derivative here, that 2 stays as a number in front. The derivative of log of 7 is going to be 1 over x, natural log of 7. So we get that as a derivative. Find f of x, f prime of x, if this is 7 square root of x, e to the x. Again, anytime you have those square roots, rewrite it as something that you can do the derivative of. And what derivative rule are we going to have here? It's going to be a product rule. Can you see that there's two functions of x multiplied by each other? The 7x to the half can be your first, and e to the x can be your second. So what does your product rule say? Keep one of them the same, multiplied by the derivative of the second one, which is just e to the x, plus keep the second one the same, multiply by the derivative of the first one, so that half comes out in front, subtract 1 from the exponent, and we have our derivative. Okay, the next couple I'm going to get you to try, and I'll put up the answers in a bit. You can check how you did on the first one. Again, the first line is all you would need to do, but if you're wondering how might the answer book at the back of my calculus book have written this one, it would have looked through this, it would have simplified this in the first set to just 3x. And then it would have looked through and said, hey, there's a 3x in common in both of those. So it would factor that out. So your answer in the back of your book might look like the bottom, and there's just a way that you could algebraically manipulate. The number one algebraic manipulation thing that comes up over and over again is factoring out a common factor. Should I go back? Was that too fast? That was good? Are you done this one already or not yet? Yes? Okay. Notice on the top of this one, there is no common factor. We can't cancel out this x squared minus 7 with this x squared minus 7, because this minus sign groups this all as one big term right now. And only if you could factor out an x minus 7 out of the whole thing could you simplify with that term on the bottom. I know, it was so sad. Anyways, here is the next one. Remember this notation, d dx just says find the derivative of what's in the brackets. This is a quotient rule. This would be one that your textbook would have a different answer in the back of the book. So what would they do? They would say, on the top, on my two terms, is there something in common? Yes. I could factor out what? I could factor out an x to the 4. What would I be left with? Well, here, this is a negative x to the 4, so you would just be left with a negative 1, minus, and there you'd still have the 5 and the 2 minus the natural log of x. And on the bottom, you have an x to the 10. Well, now that you've factored out that x to the 4, you can simplify, because that x to the 4 will cancel out completely with 4 of those, leaving you with x to the 6th on the bottom. And that's what your answer would look like when you check your answer at the back of the book. Well, yeah, they might distribute this. And negative 11 plus 5 natural log of x over x to the 6th. So it might look like that. So it's just a matter of saying, well, what could I simplify? Is there a way that I could factor out a common factor and simplify this further? But the big thing is to be able to say, if this is what they want me to get, can I perform the algebraic things I need to make that happen? And on your quiz on tomorrow, I'm going to have some of those with your quotient rule, where I'm going to say, I want your final answer to look like this. So your job is to show how to do that. Okay, first we can change this equation or hit it with a blue pen. There we go. What kind of rule is here? Chain rule. You've got an x to the half inside of an e to the x. So you do your derivative of the outside function, which means everything stays the same. And then multiply by the derivative of the inside function. Yes? I'll put up the answer for this one. Did you see the product rule? Did you see the chain rule in the natural log of 5x? Because you've got a 5x, that's your inside function, inside the natural log. What happens with the 5 and the 5x? That's what I think makes this one so interesting. They cancel out, right? And you just get, that the derivative d dx of the natural log of 5x is equal to 1 over x, which is the same Can anybody tell me why that is? Magic. Is it true if I do the derivative of the natural log of, say, 88x, is it going to be 1 over x? Yes. Why? I mean, you can explain it with the chain rule, because the chain rule will be always 1 over 88x times by 88. But can you explain it without the chain rule, why that happens? Right, but then shouldn't this change the bottom number then?
No, because if say x was 2, 88 times 2, that's whatever number it is. But if you can also have that the 88x could be whatever 88 times 2 would be. And they're both
Right, but we have things like using that same argument, why are these derivatives different? This one's 2, this one's 3. Okay. It has to do with the ln, something special with ln, yes. Natural log of 88x is equal to what? Do you agree? What? I haven't used my log laws for at least 6 months, so I've forgotten them completely. You remember that log law? Oh. If you're multiplying inside a log, you can add. So now if I take the derivative of this, or the derivative of this whole thing, natural log of 88 is a number. The derivative of a number is 0 plus 1 over x. So there's another reason why all of those ones just become 1 over x. But it has to do with the log laws. Okay, sorry, I'm getting off topic again. Excited about these questions. Straightforward one. Chain rule, what's the inside function? 1 plus 6x. So we do the derivative of natural log, which is 1 over, keep the inside the same. So it's 1 over 1 plus 6x, then multiply by the derivative of the inside, which is 6. So the e to the x to the 4 is a chain rule. The inside function is the x to the 4. The outside function is the e to the x. At the bottom there, I just showed how that works with function notation. If you made your inside function x to the 4, can you see how it's inside of the e to the x function using that function notation? Yeah? So to start with, you would rewrite this. I wouldn't use, it's not wrong if you use the quotient rule here. But I wouldn't use the quotient rule because on the top I don't have a function. It's just a 2, it's just a constant. So then, to me, it makes more sense to bring that whole bottom part up to the front by using a negative exponent. It's not wrong if you use the quotient rule. You'll just have a 0 when you do the derivative of 2. So in this case, when I bring the negative 1/3 out in front and subtract 1 from the exponent, I have a chain rule. And then in the chain rule, I have another chain rule. Because 7 plus e to the negative 3x is in the inside function at first. So when you do the derivative of that, you find out that you have a negative 3x inside e to the x. And so you have the chain rule twice here.